In previous lectures on rigid body, what we have seen is that if you have a rigid body rotating about an axis, let us take our origin here, then the angular velocity omega is a vector quantity. And any vector which is attached with the body or rotates about the axis. Because this vector is rotating, there is a change in the vector. Here I have taken vector r, so dr over dt because of this rotation is omega cross r. We have fixed the convention of direction of omega, and this is purely by rotation. The direction of omega is such that if the body is rotating along the fingers, the thumb gives the direction of omega. This equation is true for any vector, not just r. So, in general, any vector that is rotating about omega, its rate of change is given by omega cross a, and I am writing rotating here to indicate that this is purely due to rotation. Using this, therefore, when a body rotates with angular speed, angular velocity omega, this is the axis, this is the origin. You see, I am specifying origin all the time because we always take angular momentum or any quantity with respect to the origin. Then the angular momentum L, which is defined as summation over all the points in the body which are moving, mi ri cross vi is written as summation I mi ri cross vi is dri dt, and this is purely by rotation, this quantity, and this we worked out comes out to be I xx omega x plus I xy omega y plus I xz omega z in I direction plus I yx omega x plus I yy omega y plus I yz omega z in j direction, y direction, and I zx omega x plus I zy omega y plus I zz omega z in the z direction. Let me write it as k, where x, y and z directions are given, x, y, and this could be your z direction. And therefore, in general, to calculate the angular momentum, I need all these quantities. The diagonal elements Ixx, Iyy and Izz are the moments of inertia about the x-axis, about the y-axis, and about the z-axis respectively, and these quantities, the off diagonal elements, are the products of inertia. So, in general, it is quite a quantity to calculate. However, what we learned is that there is a simplification and that is about any point in a rigid body there is a set of x, y, z axis there is one set which is in one particular direction, so that all off diagonal elements I x y, I y x, I x z, I z x and I y z, I z y, these anyway are equal, but they are all equal to 0. So that the angular momentum is now quite simple, and let me change, instead of x I am going to call it x is 1 omega 1, 1 denotes x direction, so omega 1 is a component of omega in x direction, I plus I 2 omega 2 j plus I 3 omega 3 k. So the expression really gets simplified. The only catch now is that these I, j and k unit vectors are along the principal axis or principal axis 3 x y z of the body. Now principal axes are going to have a fixed orientation with respect to the body, and therefore these axes are attached with the body. As the body rotates, these axes also rotate. So that is the catch. So we have to take care of that somehow or the other when we develop our dynamics. But this is quite a simplification, that for a given body, suppose these are the principal axis x, y, z, then the angular momentum is going to be given as I1 omega 1, and for now let me now change this to 1, 2 and 3 in this direction, plus I2 omega 2 in y direction, plus I3 omega 3 in k direction. This is diagonal. Notice, however, if I1, I2 and I3, the three moments of inertia are not equal, then L is not parallel to omega. So if suppose this is omega, so that it has components in x, y and z directions, 1, 10, 2 and 3 directions, this could be L. Even if we take omega to be a constant, and even if omega 1, omega 2 and omega 3, that is the components of omega along the principal axis omega 1, omega 2 and omega 3 are constant, L is going to change, because L rotates. About omega. Why does it do so? Because L1 equals I1 omega 1, L2 equals I2 omega 2 and L3 equals I3 omega 3. All three are constant because of omega 1, omega 2 and omega 3 remaining constant, but the principal axes are themselves rotating. So these components, although they are fixed, they are rotating, and therefore L itself rotates about omega. So what we see is, in the case of x, y, z, principal axis omega and L not being parallel to omega, L could be I1 omega 1 I plus I2 omega 2 j plus I3 omega 3 k. All these numbers may remain unchanged, but L is going to rotate about omega, because the principal set of axes being attached to the body are rotating about omega, and the rate of change because of this rotation is going to be omega cross L. We will see a few examples of this kind later in the lecture. But before that, let me also for completeness show you what the kinetic energy of a rigid body is when it is rotating. So, let us see, the kinetic energy by definition is equal to summation mi vi dot vi, which I can write as 1/2 summation over I mi vi dot omega cross Ri. This is a dot product of a vector with a cross product. So, I can use the permutation formula and write this as 1/2 summation I omega cross Ri cross Vi, and Mi is always there. Since this omega is constant, summation Mi Ri cross Vi is L. This comes out to be 1/2 omega dot L. So, the kinetic energy of a rotating body is equal to 1/2 summation omega dot Ri cross Vi. I am deliberately writing Mi on this side, and this summed over is L, which is 1/2 omega dot L, and using L equal to, in the principal axis notation, omega 1 I1 omega 1 I plus I2 omega 2 j plus I3 omega 3 j k. This comes out to be 1/2 I1 omega 1 square plus 1/2 I2 omega 2 square plus 1/2 I3 omega 3 square. So, you see, if I work with the principal axis of the rotating body, my expressions, it becomes simple. Added complication is that now the principal axis itself is rotating with the body. So, we have to now look at how to handle this. Now, as an example, let me go back to our old friend, a light rod with masses m on both sides, rotating about an axis, and let us fix this axis on some ball bearings here. Let this height be z, let this also be z, let this angle be theta, let the length of the rod be 2L, so that half of it is L, and I want to first calculate L, the angular momentum of the body. Remember, we calculated this last time, but I want to do it again, and this is rotating with angular speed, angular velocity omega, like this. L in principal axis notation is going to be I1 omega 1 I plus I2 omega 2 j plus I3 omega 3 k, where these I, j, k refer to the principal axis of the body. Now, when the body is like this is a rigid body. Let me choose, this is the origin O, the x axis like this, y axis like this, and z axis is coming out. You can see these are the principal axes, and you will calculate this, we did last time, I1 to be equal to 2 ml square, that is the moment of inertia about the x axis. I2 moment of inertia about the y axis is coming out to be 0, and I3 moment of inertia about the z axis will come out to be again 2 ml square. This is omega. So, omega has two components. Let me go to the next screen and show you. This is the body, this is omega, this is theta. I1 is equal to I3 is equal to 2 ml square, I2 is 0. Let me remind you, this is my x axis, y axis and z axis coming out, and as I said earlier, as the body rotates, these axes are fixed in the body. These axes will also move. So, the components really refer to the components at the time when this rod is in the plane of this screen. So, omega 1 you can see is going to be in this direction is equal to minus omega sine theta. Omega 2 is along the y axis is going to be at this point omega cosine of theta, and omega 3 is 0, and therefore, I get L is equal to I1 omega 1 gives me minus 2 ml square omega sine theta I, and rest of the other two are 0, because I2 is 0, it gives you 0 with this, and omega 3 is 0. So, the angular momentum is in this direction at this point. At this time it is in this direction. As the body rotates, it will also come out of the plane. It will come out and go in again like this. Now, you see, as far as the mass, length, omega and sine theta, these are concerned, these are constants. So, the magnitude of angular momentum is going to be 2 ml square omega sine theta, and magnitude remains constant. So, the only change in omega occurs because it is rotating about an axis. L. So, change in L is going to be equal to omega cross L, and in general I can write this as omega 2 omega L3 minus omega 3 L2 I plus omega 3 L1 minus omega 1 L2 J plus omega 1 L2 minus omega 2 L1 K, which in this case can be calculated to be omega, let me write it further, omega 2 omega 3 I 3 minus I 2 I plus omega 3 omega 1 I 1 minus I 2 j plus omega 1 omega 2 I 2 minus I 1 k. So, what we notice is that in general, purely because of the rotation, only because of the rotation, the quantity, because L is rotating about omega, this comes out to be omega 2 omega 3 I 3 minus I 2 along the principal axis x plus omega 3 omega 1 I 1 minus I 3 j plus omega 1 omega 2 I 2 minus I 1 k at any given instant. And in the case of this rod that we took, L is in this direction. So, at any time L is equal to minus 2 m L square omega sine theta I, omega is in this direction, omega cross L, you can see will come out to be coming out of the paper in direction 3. This was 1, this was 2 and 3 was coming out. So, it will be omega cross L, omega is this way, would come out in direction 3, and its magnitude is going to be magnitude of omega magnitude of L times sine of this angle, this is theta, this is 90 minus theta, so sine of this angle is going to be cosine theta. You will see this will come out to be 2 m L square omega square sine theta cosine of theta in the direction k. Do we get the same answer from this? Of course. You can see omega 3 is 0, so these two terms, the first term and the second term, are going to give me 0. The third term gives me omega 1 times omega 2 times I2 minus I1. I2 is 0, so it comes out to be I1, which is 2 ml square with a minus sign, times omega 1. Omega 1 is minus omega cosine theta, so that comes out to be omega cosine theta. Omega 2 is omega sine theta, another omega sine theta, and the answer. So let me write it explicit. So what we got in this rod, if it is rotating like this, this is L, and therefore dl dt, which was omega cross L, came out to be 2 ml square omega square sine theta cosine theta k. On the other hand, if I calculate it using tau 1, which is dl1 dt, purely due to rotation, it is going to be omega 2 omega 3 I3 minus I2 comes out to be 0. Tau 2, which is dl2 dt, which is equal to omega 3 omega 1 I1 minus I3 will also come out to be 0. Tau 3, which is dl3 dt, is equal to omega 1 omega 2 I2 minus I1 will come out to be this. So the torque is in this direction, and therefore to keep it rotating, I have to keep applying a torque. As the body rotates, the torque direction also changes, and the torque is provided by these bearings here. If this height is z and it is symmetrically placed in z like this, then at this point, when the body is in the plane of the screen, the force here would be like this, and the force here applied by the bearing on the axis would be like this, so that there is a torque coming out of the paper, and the magnitude of the torque will be equal to 2 Fz, where F is this force, and therefore I can also calculate how much is the force applied on the axis by these ball bearings. There is another way of looking at it. The same body, when it is in the plane L, we had seen is like this, and the body is rotating like this. L has two components. Let me call it L vertical, which is along omega, and L horizontal. This is going to be, if this angle is theta, L sine theta, this is going to be L cosine theta. As the body rotates, L is also rotating about it. Its magnitude is constant. You will see that this component along omega, this component remains unchanged. The only component that rotates is his horizontal component. Let us see how it rotates. This is the horizontal component LH, and it is rotating like this. So at any given time, the small change in the vector is going to be this way, and this is going to be equal to the rate of rotation omega, that is a component perpendicular to omega, so it is rotating with omega LH delta t, and therefore delta LH over delta t magnitude is going to be same as delta L over delta t magnitude, because it is only the horizontal component that is changing, and this is going to be omega times L horizontal, and this you can see is going to be, L was 2 m L square omega sine theta, this is 90 minus theta. So, L horizontal is going to be sine of 90 minus theta of this, which is cosine of theta times omega, which comes out to be 2 ml square omega square sine theta cosine theta. And at this point, when the body is in the plane of the screen, horizontal component is going to be coming out of the screen. So, that is the direction, 3 direction of dl dt, and this is going to be the torque required. Let us now take another example that we did last time, that of a rectangle moving about, rotating about its diagonal. The length of the rectangle is A and the width is B. Let us take our origin to be its center. Then it is easy to see by symmetry that these are the principal axes. Let us call this x axis, let us call this y axis, and z axis is coming out of the plane. If the mass of the rectangle is m, then I1, that is Ixx, is going to be m a square over 12. I2 is going to be m b square over 12, and I3 is going to be m over 12 a square plus b square. And therefore, the various angular momentum component are going to be L1 equal to, suppose this angle is theta, then L1 is going to be m a square over 12 omega cosine of theta, and you can see cosine of theta is going to be this divided by this. So, this is going to be m a square divided by 12 omega cosine theta is going to be b divided by the square root of a square plus b square. Let me redraw the whole thing. This is the diagonal. This is how the plane is, axis 1, axis 2, this is theta, and this is rotating with omega, and therefore, L1 comes out to be m a square divided by 12 omega cosine theta, which is b over square root of a square plus b square. Similarly, L2, this is axis 2, is going to be coming out to be m b square over 12 omega sine theta, which is a divided by this a over square root of a square plus b square, and L3 is 0. So, you have gotten L1, L2 and L3. You can see right away that L is not parallel to omega. How about the torque? To maintain this rotation, the torque would be equal to, we can use different arguments as we used earlier. Right now, let me just use L horizontal times omega. That is, if I calculate the horizontal component and multiply by omega, it is only the horizontal component of L that is rotating, and vertical component that along omega remains unchanged. So, L horizontal is going to be L1 times cosine of this angle, which is really, this is 90 minus theta. So, sine theta. So, m a square over 12 b over square root of a square plus b square times sine of theta. Sine of theta is a divided by square root of a square plus b square. That is in this direction. The two component would have a horizontal component going in this direction. So, it will be minus m b square over 12 a over square root of a square plus b square times b over square root of a square plus b square times omega. Let me rewrite it. So, I have this body, this is L1, L2, L1 horizontal component is m a square over 12 omega sin theta cosine theta, which I can now write as ab over a square plus b square. L2 horizontal is mb square over 12 omega sin theta cosine theta, which I can write as ab over square root times divided by a square plus b square. There is no square root. This you see from the last screen. This all the product ab divided by a square plus b square, ab divided by a square plus b square times omega. And therefore, L horizontal is going to the right is equal to m a b over 12 a square plus b square a square minus b square. And therefore, the torque, which is L horizontal times omega, is going to be, or times omega, m a b over 12 a square plus b square a square minus b square times omega square. How about the direction? This is rotating like this, so this will be going into the plane, and that will be the direction of the torque. Suppose I fix bearings on the top and the bottom. To get torque going into the plane, I would need a force which is like this here and like this here. The net force is 0, but it gives a torque which is going into the plane of the screen. So, this is the torque required to keep the rectangle rotating with a constant speed omega. Let us now see how I get the same answer instead of using these horizontal component from the general expression which told me that tau 1 is equal to only by pure rotation omega 2 omega 3 I3 minus I2, tau 2 is omega 3 omega 1 I1 minus I3, and tau 3 is equal to omega 1 omega 2 I2 minus I1. Again recall, this is what we are talking about. This is the way the rectangle is. Since omega is this way, this is 1 at this point, this is 2, 3 is this way, omega 3 is 0, this comes out to be 0, this comes out to be 0. How about tau 3? It comes out to be omega 1, which is omega cosine of this angle. So, this will come out to be omega cosine of this angle is b over a square plus b square square root times omega 2, which is omega sin theta, which is omega a over square root of a square plus b square times I2 minus I1, which is m over 12 b square minus a square. So, this gives me the same answer, m a b over a square plus b square 12 omega square b square minus a square. This is, remember, third component. This is negative, means is going into this plane of the screen. So, this gives me the right direction as well as the right magnitude as we calculated earlier, which was this. This was a square minus b square, but it was going into the plane. Similarly here, since axis 3 is coming out of the plane, I get a negative tau 3. So, that means torque again is going into the plane. As a variation on this problem, let me ask you to do problem where this plate is kept at, the rectangle is kept with its plane making an angle with the vertical, and it is being rotated like this. I want you to calculate, so that it is normal to the plane is at an angle with the rotation axis. I want you to calculate how much torque would be required to keep it rotating. I leave it for you to solve, although I am going to solve a related problem, that of a disc tilted at an angle from the vertical and rotating like this, so that it is perpendicular to the disc, makes an angle theta with the axis of rotation. I want to calculate how much torque would be required to keep it rotating at a constant omega. Again, you see, now I will take this middle point, center of the disc, as the origin, and see that this one of the diameters is a principal axis, so is the other diameter, and third axis is going to be coming out of perpendicular, so it will be in this direction itself. This is direction 3, and I want to calculate what its angular momentum is and what is the torque required to keep it moving. So let us make this picture again. This is a disc rotating with this perpendicular at an angle theta with omega. This is axis 2, this is axis 1, and this is perpendicular is axis 3. You can see I1, we had calculated it earlier. The moment of inertia about one of the diameters is m, if the radius is r, square over 4. I2 is also going to be mr square over 4, and I3 is going to be mr square over 2. Omega has components at this point in direction 2 and direction 3. Omega 2 is equal to omega sine theta. Omega 3 is omega cosine theta. If I want to calculate torque, tau 1 and omega 1 is obviously 0. Omega 2, omega 3, I3 minus I2 gives me I2 minus I3 is mr square over 4, omega square sine theta cosine theta. Tau 2 is going to involve omega 1, omega 3, whatever, this gives you 0 because omega 1 is 0, and so is tau 3, which is also going to involve omega 1, and that is also coming out to be 0. So in this case, the torque is going to be in the direction along 1. At this given situation, the direction 1 is going to be coming out of the plane of the paper. So let me make it again. Let us look at this disc in the position when it is like this. 1 is coming out of the plane, 2 is like this, 3 is perpendicular to the disc, and it is rotating like this. This angle is theta, and we see in this case that the torque is coming out to be tau 1, which is mr square over 4 omega square sine theta cosine theta, as we saw in the previous slide. Tau 2 and tau 3 are 0. So torque direction is this, coming out of the plane of the paper. So if I have bearings here holding this, the force is going to be this way and this way. Let us look at the same thing again from by taking the horizontal component of the angular momentum. The angular momentum is going to have no component in direction 1 because omega 1 is 0. L2 is going to be mr square over 4 times omega sine theta, and L3 is going to be mr square by 2 omega cosine of theta, and therefore let me make it again. 2, and at this point 1 is coming out, 3 is like this, L1 we saw is 0, L2 is, this is omega, this is theta, L2 is mr square over 4 omega sine theta, L3 is mr square by 2 omega cosine of theta. So, L horizontal is going to be L3 horizontal minus L2 horizontal in this direction. You can see L3 is greater than L2, and this comes out to be mr square over 4 omega square sine theta cosine of theta. This is LH will not have omega square. Tau, that is a change in L, is going to be LH times omega, which is going to be mr square over 4 omega square sine theta cosine theta, which is the same answer that we obtained earlier. Tau 1 equals mr square over 4 omega square sine theta cosine theta in direction 1, and here also we see that since this horizontal component is pointing towards the left, it will be coming out of the paper of the screen as the disc rotates, and therefore again it is in direction 1. So, through these 3 examples, what I have shown you is, even if omega is constant, L magnitude could also be a constant, but dl over dt is not equal to 0, because L is not in the direction of omega. In all these cases where we had the components of omega along 1, 2 and 3 in such a manner that L magnitude was a constant, although there was a torque applied, but dl dt was not equal to 0, and therefore there was a torque required. We could calculate the torque either by using the general equation, which was tau 1, which is dl1 by dt, purely due to the effect of rotation, which was equal to omega 2 omega 3 I3 minus I2, tau 2, which was dl2 over dt, purely because of rotation, which was equal to omega 3 omega 1 I1 minus I3, and tau 3, which was dl3 by dt, purely because of rotation, equals omega 1 omega 2 I2 minus I1, or by taking the horizontal component of L and multiplying by omega, seeing how it is sweeping around when the body is rotating. Having done these examples, now I am in a position to also explain what we saw in the demonstrations. Recall the demonstration where I had a bicycle wheel which was rotating. Let us say it was rotating like this, and when this rotating wheel was pivoted at this point, it also started going around like this, what is known as precession. Let us have a look at that. What I showed you was, here was a bicycle wheel which I rotated like this, and when I put it here, it started going around like this. When I gave the rotation the other way, it rotated the other way. Let us try to understand this. Our observation is that it is rotating. When I have this bicycle wheel and it is turning like this, you can see that it has an angular momentum in this direction. Let me call it angular momentum due to the spin. Since it is pivoted here and it is being pulled down like this, it is not moving up and down, although very slight movement is there, that we will explain later. We can, for the time being, assume that there is a normal reaction N which is equal to mg, so that center of mass does not move up and down. What this N and mg together they do is provide a torque or a couple which is equal to, suppose this length is L and this angle is theta from the vertical, then the torque provided by them is mgl sine theta. And what about the direction? The way I have shown it right now, let me make it slightly better. The bicycle wheel is like this. This is mg, this is n. So the way I have shown it, the torque is going into the plane of the screen. So this ls must change. And how does it change? It has to change direction. It has to change into, the delta L has to be into the screen. For the time being, we will assume that the spin is so large that this rotation, precession that I am talking about, does not really affect its spin angular momentum much, although in principle you should be taking components of this rotation also to describe angular momentum, but right now we will ignore it. Then you see that ls has to change going into the plane. If I go back to this demonstration, this is the direction of angular momentum, and when there is a torque applied like this, the angular momentum has to go like this. If the angular momentum has to go like this, the body rotates, and this is precisely what we see. Let us do that now. Let us give it an angular momentum in this direction, therefore the wheel has to rotate like this, and when I leave it, it rotates like this. If I give it the rotation the other way, if I rotate it like this, then the angular momentum would be in this direction. The torque m cross g is this way, so the angular momentum has to rotate in this direction, and therefore it should rotate the other way. Let us do that. And you see it goes the other way. We can also calculate the rate of this rotation. So this torque must be equal to the magnitude of rate of rotation. Suppose this rotation is at rate omega, that means the angular frequency about this vertical axis is this way, then this should be equal to omega times LH, which is dl dt. Why? Because the vertical component of L does not change, the horizontal component sweeps, as we saw earlier. Let me make a nice picture again. This is the wheel, this is L spin, this is the vertical component which does not change. The horizontal component, if this angle is theta, is going to be ls sine theta. There is an mg acting downwards, there is an n acting upward. So tau should be equal to dl dt. We have already made sure of the directions by demonstration as well as by working out here. The tau magnitude is going to be equal to capital omega, which is the rate of precession, times L horizontal, and this we calculated to be mg L sine theta, and this should be equal to omega L spin sine theta. Sine theta cancels, and therefore you get L spin is equal to mgl divided by omega L spin equals this, and therefore omega equals mgl divided by L spin, and that's your answer. No matter what angle it is at, the precession frequency is the same. If very high spin rate is there, omega is going to be very small, and therefore I ignored any effects due to capital omega, which is generally known as gyroscopic approximation. The second demonstration that I am going to explain now is going to be this gyroscope, and what we had noticed in this gyroscope was that there are three independently rotating objects. One is this frame which can rotate about this horizontal axis, one is this frame which can rotate about the vertical axis which is mounted on this frame, outer frame, and there is this wheel. And what we noticed was, suppose I give it a spin and then rotate the outer frame, the spin tends to align with the spin direction of the outer frame. Let us see it again. I will give it a rotation, and as I rotate this, it tends to align with this. Let us try to understand this in terms of angular momentum. What I have is, I will try to make a picture. There is an outer frame like this, which can rotate about the horizontal axis. In this outer frame, there is an inner frame. Let me make it like this, which can rotate about this vertical axis, and in this inner frame I have a wheel which is like this. Let me look at it from a different view. The outer frame is like this, and let this frame, inner frame, be in the position like this, you see this way, and then the wheel is mounted like this. Suppose the wheel is given a rotation, a spin by omega, and we rotate after that this with omega. What we see is this whole assembly, inner assembly, rotates in such a manner so that the spin wheel aligns with this spin. You see that again. Let us understand why that happens. When it is rotating like this, you will see that this has an angular momentum going into the plane. As soon as I give the outer frame a rotation, this angular momentum would tend to go down. So, as soon as I rotate it like this angular momentum develops a delta L going down. However, assuming everything is frictionless, there is no torque on the system taking it, which can change angular momentum going down. If there is no torque, there should really be no change in L as far as the vertical direction is concerned. So, what does this frame do? It rotates in such a manner so that it develops a corresponding delta L in this direction, in order that net change in the angular momentum is 0, and that means it will tend to rotate like this. This frame would come out here and go in here, so that it develops an angular momentum in this direction, and that is why this whole thing aligns with omega. Having qualitatively understood this, that is, if we have these frames, this can rotate freely about this can rotate freely about this, and this can rotate like this. Why this spin aligns with the outer spin? Let us try to make it quantitative. To make it quantitative, let me make this outer frame, let me make the inner frame, and let this wheel, inner wheel, be such that its axis is making an angle theta with this direction, making an angle theta coming out of the plane of the screen. If this angular momentum is Ls, that is the angular momentum of the inner wheel, this wheel spin is Ls, its horizontal component coming out of the screen is going to be Ls sine theta, Ls horizontal. I am assuming it is making an angle with this. So, what I am assuming is, here is the axis, and this fellow is making an angle like this with this axis. So, this angle, so therefore, the component in this direction is going to be Ls sine theta, and along the axis is going to be Ln cosine theta. Ls sine theta, if this theta is very, very small, is going to be roughly equal to Ls theta. Now, when I give the outer frame a rotation, you see this component changes. This component develops a delta L in this direction. And how much is that delta L? You can see this is horizontal, is going to go down, is going to be outer omega times delta t times this component itself. So, delta L is going to be equal to Ls theta times omega delta t, this way. However, there is no torque in this direction, and therefore, delta L in this direction should be 0. What would happen? This frame would rotate in this manner so that it develops a delta L in this direction. So, it will gain an acceleration or a velocity in this direction, so that this delta L gets 0, and that gain should be delta L is equal to I, whatever I is about this axis, theta double dot, because it is going to go that way, it will change theta, times delta t. This is I omega in the direction opposite to theta, and therefore, I should have I theta double dot delta t is equal to minus L spin theta omega delta t. This cancels, and I get an equation for theta. Theta double dot is equal to is plus Ls omega over I theta is equal to 0. This is like a harmonic oscillator equation, and therefore, if it is spinning and I make an omega, it should oscillate about that omega axis. Let us see that. Here is a small angle. Let me give it a spin like this, and let us rotate the outer frame, and you see this is oscillating.